can enable a big array of application, ranging from sleep quality to monitoring for abnormal body parts movements during sleep, such as restless legs. And many systems have been proposed so far using different sensors, such as pressure sensors, light sensors, ultrasound, and load cell sensors. We're trying here to propose a system that is accurate and obtrusive and easy to install and robust. We're trying to propose a system that requires nothing from the subjects. You basically feel nothing when you lie on the bed, and the system can accurately detect and classify your motion during sleep. And one option that could be that could be useful for the system is the wireless. So we kept all these options in our system, and we're trying to have a very accurate and it's low cost also and wireless system. Our main idea is using our sensing unit, which I will explain later. And we put this sensing unit under each bed leg, and we transmit. The sensing unit has some wireless unit that transmit the data wirelessly to the receiver. And this sensing unit basically will detect the distribution of weight during movement, during motion. So the data will be collected in the receiver, and when we will do the signal processing and calculation stuff to know when exactly we have a motion and what kind of motion. So we have three main contributions in this study, in this dissertation. The first one we call motion scale. It is basically a system that detects the motion. We call motion scale because we have a motion and we have a sensor that is basically came from scale that measures the weight. We're using a load cell for that system. And the second contribution we call motion tree. It is basically the a kind of machine learning system that classify every motion, every movement on bed in the classes that I will explain. So we have 9 classes for motion. And we propose another motion using another sensor. We call it Geophone. Geophone is very sensitive to any vibration or any shaking. So we're trying to detect motion using this sensor also. Start with motion scale. Motion scale basically based on load cell. Load cell is the same exact unit that's used in bathroom scale, the scale that we use to measure our weight, the normal one. This unit has resistors inside that it's very sensitive to any force applied on it. With the force that applied, the resistor will change, so the current will change also, and we know how much force applied on that unit. According to that, we can know how much weight on that unit. The unit that we use in our system, it's very cheap. We're using 4. Every one costs about 70 cents. The overview of our system. So we have 4 load cells that every load cell connected to some amplifier circuit, and the wireless unit, or the unit that transmits the data wirelessly, we call it PIP tag. It's here in our lab. So we have 4 load cells that each one connected to a tag that transmit the data wirelessly to our receiver. We collect the data. We do some pre-processing steps because we have 4 signals now instead of 1. We have to do some processing to, I have to skip these steps because I already explained to my committee in my proposal, and it takes a very long time, but anyone interested, I can explain later. I will just explain briefly. So we have to do some pre-processing step on these 4 signals to get them ready to be for our features to be extracted. These features are used to know exactly when we have a motion. That's the main idea of the first contribution in our system, which we call the motion scale. So we have 3 features: zero crossing, energy, and log scale. With these three features, we can detect movements. We can also classify. We have some ideas about classification, and we can estimate the weight. This is the real system that we have. Anyone interested, I can show. This bed leg, and this is the load cell. It's connected to the amplifier circuit. Amplifier circuit connected to the tag that transmit the data wirelessly to overseer. So the features that we use for detection, I just explained zero crossing energy and the log peak. I go briefly with that. This is the signal, the output of the pre-processing step. We have many steps before to reach this. So this is basically the signal we get whenever we have, like this is a real experiment. You see these oscillations, they are connected with motions. People usually with these oscillations have moved. So according to that, we can find a motion whenever we have oscillation. So zero crossing basically counts the number of the time the signal crossing the zero axis, and we count that number as we reach some values whenever we have a motion. We can know that applying some threshold. We'll talk about that. Applying some threshold. So whenever we have some value with some specific value, we can know that the exact time for that value we have a motion. That's the first feature. The second feature is the same output from the pre-processing step. Whenever we have oscillation, we can see that the energy for that portion of data is higher than the rest. So if we find the energy for that signal, we can find some peaks with associated with these oscillations. Applying the thresholds also, we can find the motion. Should I stop or?
No, keep going.
Okay. Applying the threshold, we can find the peaks that already mean the motions or the oscillation. The problem with the previous two, sometimes we have very tiny, we have small motion, that's not easy to be detected or seen by the previous two features. So we applied some log scale to amplify the small motions and keep the large motion seen. This is the best feature we have. So that's kind of squaring the signal that this signal, we square it. We apply log and we have some filter with 0.2 Hertz. We can see we have a very clear peak now with every single motion, regardless it's big or small. Big means like you turn, roll your entire body. And small means you move your head, your hand, whatever. So you can see we have a clear peak whenever we have a motion. Applying, we evaluate this system by applying different set of thresholds for each feature. We can see that we can detect movement using a log, which is the best one, with an error rate 6.3, which means like we have 94% as accuracy for detection.
So do you want to explain what the X and Y axis are?
The X is the threshold value and the error rate for that threshold. So it's kind to find what is the best threshold to find motion. This 100 times cross-validation for 60% of the data for testing and 40 for training. Okay, the second contribution is we call it motion tree. This is, so basically so far we explained how to detect motion. We will use this feature as our main feature to detect motion. But now we want to know what is the kind of that motion. So we have the second contribution in our study. We call it motion tree. I will explain why we call it motion tree. So it's finer motion classification. The overview, the data collection is the same like what we had before. The data pre-processing is the same. Now we have movement detection. When we detect movement, now we have to know when the beginning and the end of that movement, because we will start getting a new set of features depending on that portion of data that we should know the beginning and the end. So features are different here, and we have some learning system that should be trained and should be tested and should be evaluated to see how accurate. The output of the motion scale using log feature is this. Now we have a peak that's already detected, and here we have the beginning and the end of that motion. So we know when people start and end their motion. That portion of data will be used to extract the new set of features. We have 20 features here. We talked about 3 features before for detection, but for classification we have 24 features. So each portion of data, each detected peak, we will extract 24 features. These features, depending on the very important thing, which is the body center of mass, the location of the body center of mass. So we have to draw our bed in some Cartesian system, and we want to know exactly the center of mass on that bed. We will know the person moves from this location to that location and extract our features, and we can figure out what exactly the body's part moved. With every movement, there will be different distribution for the weight. These are also very useful to be used in motion classification. So the first, we have 24 features. The first 4 features are the difference in the weight in each load cell. So we have 4 corners, 4 bed legs. In each bed leg, under each one, we have a load cell. We measured the difference in the weight. By the way, these values are normalized with the person's weight. So regardless your body shape, your length, your tall, your weight, all will be the same because we already normalized all the data that we have by using your body weight. So we will have the differences on the weight will depends on the motion instead of your actual weight. We have 2 other features which are the difference in the movement of the center of mass on the x-axis and the y-axis. We have a very useful feature which we call it trajectory length. This is the body center of mass before starting doing the motion. When you start doing the motion, the center of mass will move in some way depending on the way that you move. So we measure the length of during samples, we measure the length of that trajectory during your motion to have a very useful feature, which we call trajectory length. Why this feature is useful? It's useful because when you move your hand, your length usually shorter than when you turn your body to the right, you turn your body to the left. So this feature could be very useful to recognize motion from big to small. Other features is X var and Y var. We measure the difference of the movement of the center of the body center of mass for the x-axis and the y-axis according to the mean during that motion. We have the distance between the beginning and the end of the center of mass, and we have the peak value as features, and we have some other features. I'll go briefly with that, which is the real and the absolute and the square summation of the x-axis and the y-axis differences of the body center of mass during the movement. So we have the body during the movement, the body center of mass in this location. We measure the difference, the real, the square, and the absolute from the previous location, and so on during the movement. We have, according to that, we have different set of features to reach, like all of them connected and somehow, absolute, the square, and to end up with the 24 features. Now, we have the features. We have to use some tool to classify these features. We start with using SVM. SVM support vector machine tool. We should train this system and we should test it. SVM is very useful for binary classification. We're trying here to classify our body in 9 classes. We have the head, we have the hands, legs, and big motion, turning, rolling to the right, turning, rolling to the left. So we end up by 9 classes as definition. Turning, rolling to the right, turning, rolling to the left, right hand, right leg, left hand, left leg, both legs, head, and combined motions. With using SVM to classify these 9, every motion to these 9 classes, we had problems. So how to improve this tool, this technique to get a good accuracy? So instead of using one level of classification, one flat classifier, we built a binary decision tree that's based on using SVM in each node. So we kept the option or the thing that SVM is good and which is the binary classification, but we distribute our data on the tree. We use also random forest and XGBoost as another learning machine. As another machine learning techniques, I'll explain that also. So we have 3 machine learning techniques here. We have SVM, we have XGBoost, and we have random forest. We're starting with SVM. As I said, SVM is very good in binary classification. So to classify every movement to the 9 classes that we already defined, we're using one flat classifier, one level of classifier. The accuracy was 62, 63, was very bad. How to improve this one to classify every movement to each of the 9 classes that we have? We start with a big node that we call it, is the motion big or small? So we start by classifying every motion as a big or small family. Big means that you move your entire body. Small, you have move your one, or like head, hands, both hands, both legs, and so on. This classifier will distribute the data to the right and to the left depending on is it big or small. For the right side, we will classify the big family as a right or left movement, like turning, rolling to the right, turning, rolling to the left. Each node is SVM, and it's binary SVM. But if you go through the tree, we will have 9 classes using SVM in each node in a binary way. So on this side, we will have class 1 and class 2, which is right, turn, or rolling to the right, and class 2, turn or rolling to the left. For small family, we start from the idea of let's classify the lower half motion from the upper half. So we kind of asking the data, are you belong to the lower half or to the upper half? We start with legs. Is this movement includes legs? If yes, then we'll go to the legs family, or the lower half family. If no, then we'll go to the upper half family, which includes heads, right hand, left hand, or both. If it's legs, then we can know that is it right leg? If it's no, then we have to check it is it left leg or both. In this way, we kept the binary option, the binary property for SVM, and we have 9 classes. Someone can ask, why did you use this exact tree design, this exact tree structure? This tree is intuitive in some way because it's easier for us as a body part to distinguish big from small in the beginning, and upper from lower next, and so on. And is also to keep a very good accuracy. It's very useful to start with a node that has a very good accuracy, because whenever we have error, that error will propagate through the tree when we go with the data. So it's better to have a good classifier at top. If we use this design, for example, we classify legs first instead of big. Legs is not accurate by intuitive, like intuitively, rationally, legs is not good to distinguish motion as a big and small from, because somehow will combine through other motion. This will give me more errors, and that will affect the whole accuracy of the system. We measure the accuracy, by the way.
So, yeah, so one question here. So your model is, you take the same data set, you train an SVN classifier on each binary decision, right?
For big classes, all the data is trained here.
Okay, so then when you go to the other
When
side...
we go to the legs,
right.
we don't need to train it on the small portion of, on the big family
Okay,
data.
so all the data that
Appropriate for that
you
node.
throw out, and then
Yes.
you keep going down the tree.
Yes.
But each node is like a separate training phase for the classifier.
Separate.
Right.
And feature selection
Yeah.
applied to that node also.
Okay, and then you remove the data from the other class.
Yes.
Okay.
Yes. The same case, also, if we start asking about head instead of leg here, we will end up by a tree that has longer pathes in somehow. As longer we go, the deeper we go, as more error we will get. So we're trying to keep the best classifier on top and shorter tree as possible. This tree is similar in somehow to our tree, but instead of asking legs, we're asking heads. Heads has lower accuracy than legs because in somehow it's combined with hands. So we want to provide the same accuracy if we ask legs before. We end up by this tree as the best tree structure that we can go ahead with. We evaluate our system by doing many experiments. Many students here joined this experiment. We have 40 healthy adults with 70 experiments, 26 males, 40 females, and we're using the inner spring matrix, the twin size. We ask people to do 35 predefined movements, 8 of them large, involving the entire body, and 27 that only involve one part or 2 parts. This is kind of like what exactly the motion, some of them. So we bended legs, we cross legs, we put the hand on head, turn right, roll over, turn left, and so on. To evaluate our system, we pick randomly 60% of the data for training and 40 for testing, and we repeat that 500 times as cross-validation. We're using random forest in each node to select the best features. So the recognition accuracy for each class and for the whole system, we have something called recall and precision. These things usually measured in classification problems to know how accurate our system with each class. And the whole accuracy is 90%. So we can know with 90% what exactly the motion for person and bed. The flat SVN, the one level classification was 65. So with this tree, we improve the SVN from one level classifier to the tree that we call a motion tree from 65 to 90%. How about using another machine learning? Since we said like SVM is just good in binary, so we improve that tree. Why don't we use another machine learning that are good for multi-class classification? And we picked 2 famous techniques, which are random forest and XGBoost. Random forest basically builds a bunch of trees, and it takes the average of the results from that tree. So each tree will vote for something. The total is the larger voting. We use tree topology for this technique. We use a flat topology and the same tree structures that we have in motion tree, and we have 2-level topology. I'll explain what does that mean. The flat topology, the 1-level topology, is we just give the movement, and the random forest will give us one of the 9 classes that the movement belongs to. So we have a 90.8 with using this topology for random forest. By the way, random forest is very useful, but its problem is very slow in programming and training. So to train every model, it takes about a week to 10 days to end with this accuracy. With SVM, maybe you need just 45 minutes. The other topology is using the same tree structure, same tree structures that we have in motion tree. We reached and somehow less than what we have in SVM, 89.3 for the same tree structure with using random forest in each node instead of SVM. So why don't we do something in between? We don't need to this big tree, multi-level tree, and not one level classifier, not flat classifier. Why don't we keep these two options in some mixed design? So we call this design a random forest small tree. We kept the two-level tree, it's multi-levels, and one-level classifier and somehow. So we start by classifying movements into big and small, the same right side that we have in the motion tree. But here, instead of going deep and to know what exactly the motion we have, we use a flat classifier to distinguish the movement into one of the 7 classes, the remaining 7 classes. For each classifier, for example, the big can classify, its accuracy is 99.4. So it's very good to classify big from small. The right turn to distinguish from left turn or roll, it's 92.4. The small motion classifier, this one, they classify the small family into one of the 7 motion, hand, legs, and so on. It's 90.8. The total accuracy, the whole accuracy of this system is 90.9, which is the best that we have so far. With random forest, we reach this best accuracy. This is the best accuracy we got from random forest. How about using the XGBoost? XGBoost, it's similar to random forest in somehow, but instead of using multiple trees, XGBoost adjusts the parameters and the weights that it has internally with every iteration, using the previous error from the previous iteration. It also computes the importance for every feature, and depending on that importance, the weights and the parameters will be adjusted. So we use 25 iterations, 25 times for every training, and we use the flat topology only in our XGBoost system. The accuracy that we got from the recall and precision, for each class is here in this table, and the whole accuracy for the system is 90.5. Now we have explained 3 techniques: SVM, random forest, and XGBoost, with different topologies. How about putting everything together? How about combining all these 3 techniques in one final decision, instead of having 3 results? So we were thinking by using some logical combination. If we use the output for motion tree using SVM, and the output from the small tree using the random forest, and the output of XGBoost, and take 2 out of 3. So if these 3 techniques give us some output that 2 out of them are similar, we will go with that. Otherwise, if we have 3 different results, we will go with the flat topology for random forest. So this algorithm will explains exactly what I said. We have four techniques here: SVM, the motion tree, the random forest, the small one, and the random forest, the flat, and the XGBoost. So if we have 1, 2, 3 are similar, or 2 out of them are similar, we'll go with that. If they all are different, we'll take the output from the flat random forest. That improves our accuracy for each class, and we end up by 91.5 as classification accuracy. So every movement can be classified in a percentage with a 91.5 to one of the 9 classes that we defined.
So go back. So you're trying sort of like a boosting idea here, where you have like n classifiers, but you only got like what? What was the difference? Like 1.5% or something? I think it went up from like 90.
About 0.6 percentage.
Okay.
Yeah.
So it wasn't like a huge.
But that's still like
Okay.
if we have huge data, that will be useful also.
Okay. All right.
So the concluding remark for the second contribution that we have, the classifier system, we use the same hardware that we have in motion scale, the load cell sensing unit, and we classify the motion into 9 classes using 24 features and using 3 techniques, SVM, random forest, and XGBoost. And this table summarized all the classification accuracy for all the previous techniques we used. The combination algorithm boosts all the accuracy to 91.5. Our third contribution is the sensor unit. The sensor that we used previously is load cell. There are some good sensors, and also cheap, that detect the motion in somehow, because we are focusing here on the vibration, on the oscillation, on the shaking on the system we have whenever we have a movement. So why don't we use some sensor that is good to detecting these things? One of the sensors is to detect vibration is called a geophone. The geophone is basically the main sensor that's used to detect earthquake. It's very sensitive in a way. If I put it on this table and I walking or close the door, it will give some oscillation, like some electrical signal. It's basically a magnet that oscillates freely inside a coil. So that's the electricity principle. We have some voltage whenever we shake this magnet. We're using here 2 geophones, one close to the head and one close to the leg, feet. We connect them to some amplifier circuit, and using the tag also with the frequency, with the sampling frequency 30 Hertz. So we broadcast the data wirelessly to our receiver. We repeat in somehow the same pre-processing steps that we used in motion scale. So we interpolate the data, filtration, interpolation is very useful because we're using many signals, and since they are wireless, so we won't expect to get the same volume of data because of pocket loss. So we have to match all lines together by using data interpolation. And we extract features to know when we have a motion and what kind of motion. So let's just see how this system is accurate and what is the difference between using this one and the load cell. This is the real system we have. That's the geophone, and this is amplifier circuit, and this is the tag that for wireless communication. We insert that sensor under the mattress, between the mattress and the frame. So whenever the person or subject moves, there's going to be kind of oscillation through that sensor. That oscillation will be amplified and transmitted to our receiver. A geophone is different than load cell. Geophone it's kind of like dealing with AC signal. With load cell, we have kind of DC signal. A geophone has some problems, like it's very sensitive to any noise, it's very sensitive to any motion, any on the environment. So we have to deal with all of these things. And we still have to use multiple sensors, like we have 2 geophones, so we have to deal with the problems of packets loss. The same set of features are used. Here we're talking about detection, so we go back to log, energy, and zero crossing. We'll see which of these features is useful here for Geophone. This is the signal, the original signal that we get from the Geophone for a real experiment. That's from Geophone 1, and this is from Geophone 2. These oscillations represent whenever we have a motion, whenever we have somebody's part move. So you can see, because of the packet loss, for the same time, we didn't get the exact amount of data, the number of packets. So we have to interpolate the data to match them and to put them in the same amount. After interpolation, we drop the local mean. I skipped all these steps previously. Drop the local mean because our features, the log and zero crossing and energy, require a signal that oscillates around the zero axis. So, okay, the first feature is the energy. The same way we compute the energy for the signal from the Geophone, we can find a very clear peak whenever we have a motion. The same for log, which is also always the best. We have a very clear peak whenever we have a motion. Of course, we have some pre-processing steps. For zero crossing, there is a problem. Zero crossing is a very messy signal, and it doesn't reflect any information about the motions, and we couldn't use it as a good feature here. So we just dropped this feature in our study for Geophone. Because as what I said, Geophone is different than load cell. Load cell by itself is DC signal, but Geophone it's AC, so zero crossing won't be benefit. We repeat, we have many experiments, a little bit than what we have done for load cell. We have 15 subjects. We did 30 experiments, and using twin size mattress, the same exact movements we ask people to move, and we have large and small, the same. Now we have, we cross-validated, we took 50% of the data randomly for testing and 50 for training, and we repeated that 500 times. We used the video camera as a recording for ground truth. Here we have a good results for detection. For energy, this is the set of thresholds we applied and with the error rate. For energy, we end up with a 6% as the error rate, which means 94. That's what we got for load cell using log to detect movements. And we have a 2% as the error to detect movement with log feature, which is very good because we have 98, actually less than 2, to be honest, but I gave the average here. So we can know that we have a motion in the signal by using a geophone with a 98% as accuracy. What if we try to classify motion? We detect motion in a very perfect way with using a geophone. How if we try to classify these motions as big or small? Or we can go deep for more classes. So we start with 2-class classification, and we move to 3-class classification. The 2 classes are big or small, as what I explained, and the 3 classes, big, upper half, and lower half, we call legs or heads and head. Head and heads. We use 4 features: the value of the peak from the log feature from each geophone, so we have peak 1 and peak 2, and the duration or the time for that motion. So we have D1 from Geophone 1 and D2 from Geophone 2. We use, as a machine learning here technique, we use a flat random forest for training purposes. For 2 classes, to classify motion into either big or small, the geophone sensor, the geophone system using random forest, is can classify motion with accuracy of 98.5. But if we increase the classes to 3, we drop to 88. So we can say that a geophone by itself, it's very good for detection, but it's not useful for classification.
So why is that?
Why is that? Because the main feature, the main thing that we use in our load cell feature, load cell sensor, is the location of the body center of mass. We could know that the person moves from right to left by using that thing. Here we don't have any information about it. You see, this sensor just detects the oscillation, the vibration when we have motion. There is any information about the weight, the distribution of the weight on the bed, and the direction from right to left, from left to right. We just have 2 geophones that can detect, is it higher oscillation on the lower half from the upper half. That's why we have a very low accuracy when we increase the classes. So, as a conclusion, motion is, I will explain this. Geophone is a very good in detection, but it's very bad in classification because we're still missing some information about body center of mass. So with 3 classes, we reached 88. How about 9 classes? 9 classes will go very bad. So we can say that for future work, the system, the load cell sensor system, can be tested and evaluated to monitor kids or toddlers movement or elderly people. And also, a very useful step is combining geophone with load cell in one system. Geophone is very good in detection, which we read 98, and instead of 94 in load cell. But it's not useful for classification, so we can still keep the load cell system to classify movements into 9 classes. And also, using the 4 features that we already have in geophone and added to the 24 features that we have for load cell, can increase the accuracy of classification from 91.5 in the combined motion, in the combined algorithm, and combination algorithm, to some good accuracy. We believe that combining these 2 systems will give us a very accurate, still low cost, and easy to install system to classify and to detect and classify motion. All the work we have done, we have published in 3 papers so far. So we have a motion scale published in Chase conference, and some system for geophone. That's different than what we have. We improved the one that I explained. We use the geophone for heartbeat detection. We published that also in IPSN. And we have a paper that's just accepted with using a motion tree to classify motions. At the end, I would like to thank many people in my mind. First of all, I would like to thank my professor, for my advisor, Professor Yang, for whatever she did for me. Thank you so much. Thank you for your time, for your patience. And my great thanks for the great man, the blessing on my PhD journey, the light, Rich Howard. And I would like also to thank my teammate, Chenwa. Thank you so much for everything. He was great with me, he was nice, and he was there whenever I needed. And thank you for my family, my parents, my wife and kids, and thank you for all the students in WINLAB who joined this experiment. Without them, we couldn't reach these results. Yeah, I have asked them too much to do that. Thank you for all my friends here, and thank you for coming here. Thank you so much.
I'm surprised that's still your friends. All right, so any questions from the audience?
Sure.
So,
My teammate.
I guess you're taking the approach, vibration approach to detect motion. So
For Geophone?
I mean, low cell is
Yeah,
another
yeah.
form of vibration sensing. So have you considered using wearable devices like I mean,
What?
smartphones?
Oh.
Wristbands are popular.
There's kind of application that can be used. Yes, this system can be like the lower level for that system. We can broadcast the data using some system you like, and with some application you can design for phone to know what exactly the motion for someone who's sleeping in the bed that you like to know what exactly people doing. Yeah, it can be used very but you need some application, high level application for that. We haven't done that level for phone application.
What other potential applications do you think you could use this technique for?
I've just explained for future steps can be used for toddlers, kids. Some position very critical to some kids. Also can be used to detect some, to monitor people with some disease, because if you want to monitor people during sleep, with legs shaking, with hands shaking, some kind of disease, it's very hard. You have to connect many devices, you have to keep camera monitoring their sleeping. With this system, people feel nothing, and you will get exactly what part of body move.
Are there any non-sleeping applications that you can think of?
This application not necessary for sleep. I mean, to monitor what exactly, to diagnose what's the sickness you have. Yeah. But for Geophone, the story is different. For Geophone, you can improve it. We already did that to detect the heartbeat signals. We can know but that's different. That's, if you like it, you can wait
his
for
thesis?
his thesis. Yeah.
Well, you can always install the devices, the systems on a crib, right? So, and the kids, the babies stay there, and the babies are not necessarily sleeping all the time. And you can actually keep track of the movements the babies have.
And you can make a SIDS detector.
That's hard, because the accuracy has to be super high.
And you do that, I don't want to.
So I
You can
have
do activity monitoring with it if the baby stands up or
Right,
sits up.
right.
Yeah.
So that could be
Which
something.
means chairs in a daycare center to find ADD kids.
They don't move that much.
Yeah,
Okay.
right.
Okay, so Wade has a question, so I'll be the virtual Wade. If you wanted to go beyond the geophone detection, to actually classify and distinguish between people resting in a bed, what would you do? So if you try to do, right, so,
Existence, you mean the existence.
well, no, I think what his question's getting at is, if you want to distinguish, could you use your system to distinguish different people in the bed?
No,
Okay,
no. Geophone is not good with that.
So you don't think that would work?
No, no.
So my question is,
Oh.
what would he do go beyond geophones?
Okay, so he said, what would you do to go beyond geophones?
So
I
you-
want him to solve the problem. What would he do? He's an engineer.
So you want to know if let me repeat your question another way. You want to know if the subject is a kid or big or adult or fat or thin, tall or short or somehow?
Somehow tell the difference between Yan Yang and myself.
With
On
the
that bed.
with the geophone by itself, there's no way.
But you now have a $10,000 budget to come up with whatever system you want.
If I have that, I will add load cells to the geophone to know the missing information. There is dimensions missing with geophone. Geophone is good to detect motion, to detect vibration, but we cannot know the size of the source that causes this motion.
Okay. And how will load cells do that for you?
With load cells, we have the weight. We have the weight, where we can know the weight of the person on the bed.
All right. But let's say you find two people of almost the same weight. How would you distinguish between those two people?
Okay. They both sleeping at the same time?
No, today versus tomorrow.
Okay, I can know the weight. From the weight I can know that this is adult and this is a kid. We have, I mean, I didn't go deep with the weights meaning, but by, I mean, if it's like 70 pounds is different than 124, right?
Yes. So is it only weight that becomes the distinguishing factor?
For load cells, yes.
Okay.
Yes.
All right.
Well, let me push on Wade's thing, because you're supposed to be a PhD. So what's the, so you said Geophone, you couldn't discriminate between different people. Okay.
Yeah.
So I think you have a hidden assumption there. So what's the assumption that you're making that you can't discriminate between
Okay.
different people?
If I put the Geophone here,
Yeah.
you and I will knock on the table. We may get the same vibration.
Bay.
No one can know, you or me, who did that.
Right, but if somebody's sleeping in the bed,
It's the same case.
is it true that the vibration signature between different people is the same?
No necessary. No necessary.
If that's true, then
No necessary.
could you use Geophone to discriminate between different people?
I mean, what is exactly the difference that you're looking for?
Well, right, let's say, I think getting at Wade's question, right, let's say that, you know, one day it's person A and the next day it's person B.
For identity,
Is it true that the vibration signature is constant between person A and person B?
for different person, the same time is not, different times it's not the same. For the same person, different times, I move my head.
Right.
This time strongly than I moved it
Right,
previously.
so what if I gave you hours to discriminate? Could you do that?
I haven't tried.
What would be your intuition? If I said, let's say overnight, I give you 8 hours of data per person.
I have to try. I have no answer. I have to try.
Okay.
It could be work.
So you don't have an intuition on that?
No.
If it doesn't work, what kind of things will you be doing to make it work better? Think along that line. It's not an answer of yes, it will work, or no, it will not. But let's say if it doesn't work that well, right? Then what will be your next step to fix it?
Yeah, I think about it. But that's a different story. I haven't even think about that.
Okay.
Well, I thought you dropped the mean, right? Will that be able to
The mean for the signal?
mean weight?
The mean, okay, so it's still weight. But weight is, maybe we have a very, two
Well,
people.
two people that are different in weight.
And somehow what if they are and somehow comparable? Somehow close to each other. We still cannot have a good idea who is sleeping now. Is this female, is it male? I don't know.
Okay. All right.
Okay. So it's a
Cut that
que-
off in the closed section. Okay.
Okay. So, right, so I think, given all the students here, they should probably hear this question. So, you know, machine learning is this really hot topic, so you have some experience with it now? Okay. So, you mentioned a little bit about, or these, right, there was you use SVN, right, you use a boosting, extreme boosting. If you were gonna give advice to students coming behind you about how to approach using machine learning to do this kind of classification, what would your advice to them be?
If you have a binary classification, you can use SVN. 2 classes, SVN is good. But if you have multiple classification, you can use XGBoost. Random forest is very good, but takes long time to be done, to have your models trained and done for testing. XGBoost is very fast, very, very fast. And is somehow very close to random forest.
Right, so there's another approach you used with SVN, which was you had to hand create the tree, effectively a binary tree. Would you recommend, and you got pretty good results, and I guess it didn't train, although you had this step where, like in the other classifiers, they would just build the trees from the data.
Yeah, why not? I mean, SVM,
So-
it's easiest to train, and SVM, you can go with the data. when you build your system. You know where you have some problems. For example, in our tree, we have always problems with the leg node. Kind of people when they move their hands, so the system is mixed. You will miss all this information if you use random forest and XGBoost. But if you have your tree and you go deep with every node, you will know where the error exactly in your system.
Right, and so how hard was building that tree? It looked like,
It depends.
at the end you had the nice tree, but how hard was it to get there?
It depends. It depends on your application.
Okay.
Since we built this tree according to body's part, depends on your application how you can build your.
So
tree.
how hard was it for you?
How harder?
Yeah. I mean, did you start at some other place and eventually get
We
there?
were playing with the SVM and as a one level,
Yeah.
but we got the idea of why we just keep the binary and we moved in multi-level asking questions. So we built the tree.
So it wasn't that difficult?
No, just time consuming to train every node and
It was
one
pretty
time.
logical. So that's the nice thing about, sorry, I'm
That's
chiming in
okay.
again.
Okay. And then the other question, I guess, would be, what would it take, so this is sort of along Wade's line, so given your 4 load cell sensors, you were kind of like 90% accuracy? Sort of
For classification?
Yeah, for for that tree
Okay.
node, which was pretty good. What do you think it would take to push to like 99%? Like if you could add whatever you wanted.
That's a good point.
So which one is the worst and how are you going to improve on that?
Yeah, one of the problems that we have, we don't think that the system is bad, but labeling of the data by itself is bad. Because we are as a human, we thought that this subject moves his legs only.
Yeah, okay.
But actually he moves his hands also, he moves his head also.
Yeah.
But we're still labeling this data as legs only. So how many times you repeated this problem in your data? That will affect the whole accuracy at the end.
So data cleaning is
Yes.
important.
Yes, but it was very hard for us because we tried to match every movement with the videotape that we have, so we had kind of a problem. So that could be very useful to improve the accuracy.
I have a question. So what is the sampling rate we use for collecting?
Sorry?
What is the sampling rate that
30 hertz.
so can you like go higher or?
If you go higher, since we're using a wireless system with the tags, you will have a problem with the packet loss because of the collision, because of the environment, like the noise. So we try to keep something in between. We keep the body's movement frequency, which is around 4 to 6, and we keeping a good accuracy, a good sampling rate, and not high to have this percentage of. So we pick that 30 hertz. We still have some packet loss, which is 10%, but we could solve it by using interpolation.
Yes, so just let's say like there is no package loss, then would it be better if we have like higher sampling rates?
No, 30 hertz is enough for body's motion.
Okay.
Yeah.
So how low can you go to for collecting those motions?
Sorry?
So
How
for
low can you go?
How low? Okay, so we did kind of FFT for the signal from the load cell. We found there are 15 hertz component for some body's motion. So we kept 30 to cover all possible motions and to get rid from that big, huge packet loss. So we kept that number to have balance in between.
Thank you.
Do you think that adding more sensors like load cells, like making them 6 or 8, will help you to improve the system?
How many legs embed usually?
Or, but maybe you can but you are developing a new system.
If you have more legs, you can put it.
It's a good question though. You may not, could you put the load cells in places other than the legs?
Yeah, let's say one under your head.
Under the pillow.
Right?
You
Yes.
can put instead of using a load cell by itself, you can use the actual resistor that it has, the strain gauge. It has some resistor called strain gauge. You can put it under the pillow and
Pillow.
and under
So you can embed.
the sheet of
Yeah, yeah.
so it can have some information also.
Yeah, but then you will be assuming that the head will always be there. So that.
Yes, but that system, if we're using the strain, won't be the same cost that we have. Will be a little bit more expensive.
Okay.
And I'm not sure if you can keep the wireless man.
One more question. So let's assume that you are using this load cell system, okay? And you have the chance to store the information of your objects, the people who are sleeping on the bed, in some other place. So let's say that you are, so my question is that, can you figure out who was sleeping on that bed based on the signature or the information that you already stored? Because till now you didn't store any information.
So for identity detection,
Something like privacy, stuff like this, I mean.
we just have the weight. I'm not sure the weight is enough.
What about the manner of the person who is sleeping on the bed? I mean, some people are just sleeping on
That's
the right
different.
side.
That's different story. I haven't tried it. It may be useful. It may be useful.
So you can figure out who is.
It could be. I have no exact answer for this. It could be.
Yeah.
Any other questions? All right, so if there are no questions, we are going to have a closed session and to grill him even further.
Thank you so much.
Thank you.
Do you have an option to turn off the live broadcast?
I don't know,
So
wait,
you can talk to Mike.
Yes.
are you in the live broadcast thing?
Can you talk to Mike to
I'm
start
on
the
y'all, I'm on
screen?
Skype.
Okay.
To start the
Did you get a link to that?
No, I didn't try.
Okay. It's not clear it's on, but
Yeah.
That would,
Don't take
that
your
would be a good
responses off
system.
broadcast.
do you know how to turn it off from inside the room?
I want
No.
It
to.
would be sooner, unlike a lot, it would be sooner
told
enough to
Chen.
get you
Do you know how to turn it
information
off?
they actually
I don't know.
use.
Wanting to